So, second session in the morning. Kicking us off is going to be Mohammad Akbarpour, and he's an assistant professor of economics at Stanford GSB. Another person I'm very, very honored to have as a collaborator. He studies market design in all shapes and sizes, and of late in particular, interactions of market design and questions of inequality and development, and as we'll see today, networked markets. Before joining the Stanford faculty, he was a research fellow at the Becker-Friedman Institute at the University of Chicago, and prior to that, he was on a sojourn in Chicago, but he completed his PhD at Stanford, his master's there as well in economics, and before that, his bachelor's in electrical engineering at the Sharif University of Technology. So he might look a little bit familiar because he spoke here last year. So I'm going to give only sort of the update. The paper he presented here last year won the Best Paper Award at the Workshop of Internet and Network Economics. And then another paper of his joint work with Shengwu Li won the Best Paper Award at the Economics and Computation Conference. So this year he was awarded the 2 top paper awards in economics and computation. For the rest of his massive list of accolades, see last year's conference introduction. We're very excited to hear what he has to say. He's one of the deepest thinkers I know, and here he's going to give us a deep rethinking of network data and diffusion. Just a few seeds more. Let's welcome Mohammad.
Thank you. Thank you. Thanks, Scott, for always unusually wonderful introductions that at least I don't feel are appropriate for me. But anyways, thank you everyone for coming. This is a joint work with Amin Saberi, who is my colleague at the Stanford Operations Research, and Suraj Malladi, who is a wonderful graduate student at the Stanford GSB. I'm reporting the findings that these 2 people mostly contributed. So let me see if this is on. What's happening here? Oh, okay. So seems there is a... Okay, so I want to jump to the mathematical problem directly. I do theory, so I don't want to do any introduction. So here is a mathematical problem. You have a social network of n people. Think of Facebook or a friendship network in a college. And you have some diffusion model in mind. For example, if I inform Scott about a piece of news or information, he's going to talk to each one of his friends with probability p. And you have a budget of S seeds, meaning that you can inform, say, 5 people at the beginning of this diffusion process, so that you hope they're going to talk to their friends are going to talk to their friends of friends, and you're going to have this viral diffusion of information. The question is, who are the optimal S seeds? Okay, who are the people that you should inform to just boost the diffusion? And this question is simple for a network like this. I mean, if you have 3 seeds, you can visually see who are the optimal seeds. For a network like this one, which is a subnetwork of Facebook, it's not as simple. And this actually motivated Kempe, Klemberg, and Tardosh in 2003 to write a paper and prove that this problem is NP-complete. And this is one of those really NP-complete problems. It's very hard to even get close to the optimal. Now, I'm sure many of you can easily see the applications of this problem. This is one of the most widely studied interdisciplinary problems. The diffusion of microfinance in, different developing countries is an application. We want to inform some people about a microfinance product, and we expect them to talk to their friends and their friends to their friends and so on. Spread of new technologies in different settings could be an application of this. There is this group of people in University of Southern California who work on HIV prevention information among homeless youth of LA, and they are trying to find the influential nodes of the network. Word of mouth marketing is where this problem actually started. That's the origin of this problem, and then a spread of political ideas and so on and so forth. So you have this pretty important from an applied perspective problem, and it's NP-complete. What can you do? Well, that's what typically we do in computer science, that you try to approximate the solution of this hard problem. And there is I cannot exaggerate the size of this literature. There are all these papers, hundreds if not thousands of papers, that try to come up with some notion of centrality. So you don't have to know what are each one of these notions, but basically the idea is that you give me a social network, I'm going to define some notion of centrality, for example, degree centrality, who has the maximum number of friends, and I rank agents from 1 to n, and I pick the top S people. Okay, and the question here is which computationally feasible heuristic is better than the other one? Now, this is a pretty large literature. I'm not going to summarize all of these papers for you, but the conclusion of the literature can be seen in this paragraph, which is the concluding paragraph of Banerjee, Chandrasekhar, Duflo, and Jackson's paper in Science 2013, that network targeting has important implications for policymakers to pick the right people to inform in order to ensure that a new idea or product or piece of information reaches the maximum number of people. That's typically the conclusion that we get. Today I'm going to actually confirm this conclusion that these are right, but we're going to do something else too. Now, so what's our paper about? So the point is, especially when you get to economic settings like development setting, now Emily is going to talk about this point more than me in the next talk, you need the network data to calculate these measures. You have to know who is friend with whom. And network data has a ton of issues. The most obvious one is that for a diffusion of microfinance type of setting or spreading technology or information to homeless youth, it's pretty expensive to have the network data. And even if you have the network data, it's extremely imperfect. So people forget, who are their friends. I cannot remember more than 20 of my friends if you ask me now. There are issues of measurement error. So in many of these networks, a bunch of nodes have 0 friends, and the reason is that they were not available at the time of survey. And there are issues of incentive compatibility, to use some economics jargon. If I know you're going to use this information to inform someone, I'm going to introduce my cousins as my friends. So these are all issues with the network data. And then there are a couple of papers, one of which you will see after this talk, that try to address this issue by finding central agents with some limited information or reconstructing the total network with a subnetwork. And we will see about that soon. What I'm going to do today is to take one step back and see, okay, this is a data. In many settings, it's a big data like Facebook, which is expensive and imperfect and has all these issues. What is the value of having access to this data? Do we really need to solve this complex optimization problem over this expensive data? And for that, I'm going to start with a simulation. So if you want to know what is the message of this paper, just listen to me in the next 3 minutes, and then you can go and have your coffees. So the simulation is going to replicate Diffusion of Microfinance paper by Banerjee et al. And the reason for choosing this paper is that this is the field-defining paper in economics of development, in network seeding in development economics, widely cited and well-regarded. So here is how this paper works, or how this simulation is going to work. I'm going to take, or we are going to take, the network data that they've collected from 75 Indian villages. And then they have this model of diffusion in mind that they structurally estimate in the paper, that once I inform Scott, he is going to decide to participate or not participate in the microfinance program. Conditioning on participation, he is going to talk to his friends independently with probability CP. And then if he does not participate, again, he's going to talk to his friends with probability CN, and we expect CN to be less than CP. We are going to estimate it using data. It could be even 0. And then the whole diffusion process stops after cap T periods. So Scott talks to his friends talk to his friends, his friend talks to his friend, and after some number of periods, people stop talking. The program is not relevant anymore. And then they observe this experiment, basically. They observe that some people were seeded, who were informed people, and from that data of these 75 villages, they estimate these numbers, and these are the rough estimate. They have a range, so this is a midpoint of that range, but all the result that I show you goes through for all points of the range. So I'm gonna take this diffusion model with these numbers, and then take their network data, and then take what notion of centrality they introduce as actually the right notion of centrality to rank agents and seed those people, which is diffusion centrality. I mean, we don't have to go through details of that, but it's very similar to eigenvector centrality. In fact, it's between eigenvector centrality and degree centrality. So I'm going to see how diffusion centrality performs using this diffusion model in their data set. Okay. And this is the most important graph I'm going to show you today. On the x-axis, you observe the number of seeds. And on the y-axis, you see total diffusion. So walk with me. Let's start with this point to be clear what this graph is showing. If I give you one seed and you choose the most diffusion central agent, the total diffusion would be like 126. Okay, meaning that if I choose the most diffusion central agent in all these 75 villages and do that 1,000,000 times and measure the total diffusion in expectation, that's a number. How many people would be informed at the end of the diffusion process? If I choose one agent randomly, this green curve is random seeding. I just totally ignore the network structure. It's expensive, I don't have it. I'm going to randomly seed an agent. I'm going to get 60 in expectation. Okay, so this is confirming what all these papers claim. Network targeting significantly helps diffusion. So what I want you to look, however, is that here we are looking at the y-axis. I want you to look at the x-axis. If I randomly seed 4 agents, I'm already getting a diffusion which is more than centrally seeding 1 agent. Okay, so at least in this simulation, random with 3 extra seeds is doing better than network diffusion with diffusion centrality seeding. And you might think this is incidental. We replicated this on a bunch of data sets, and it worked in all of them. So we were like, let's try to prove it theoretically, and the rest of this talk is going to show that this is not incidental. There's a fundamental feature in the diffusion process that makes this happen. Random seeding with a few additional seeds, and the number in all simulations is less than 3, is going to perform better than central seeding. Yes?
You might be really concerned that if you have one random seed, you know, this is with 1,000,000, it's a
Yeah.
Could you show some error bars?
Yeah, the question is, because it's not going to be recorded what you said, the question is how about the standard errors? I'm not showing it here, but they are actually pretty small. And you will see that from the proof. Yeah. Okay, so this is the story of this paper. In one world, you have access to the full network structure. And in fact, you have access to infinite computational power, and you can solve for the solution of that NP-complete problem and inform S seeds optimally, not even diffusion centrality or whatever centrality notion you have in mind. In a different world, you're going to ignore the network structure. You have no information about the network. So let's see what's happening here. I think I can continue. Yeah, we are fine. So you are going to inform S plus X agents totally randomly, ignoring the network structure. The question is, for what value of X does random seeding beats optimum seeding? Okay, so I'm just comparing random with the exact optimum, which you don't have access to. And this is going to quantify the value of both network data and computational power. So if the answer is 3, you should think about, do you want to go and collect all of this network data and solve for the solution of this computationally complex problem, or you just want to seed 2 more people, 3 more people? And the answer, to spoil the result, is that in viral diffusions, for a wide class of diffusion models that hopefully we will talk about in the next 30, 40 minutes, random with a few extra seeds is going to beat optimum. Good. So this is the outline of the talk. I will tell you a very simple diffusion model. You're going to criticize the diffusion model and network model a lot because they are too simple, but hopefully we will extend them if we have time. And then I'm going to tell you the main theorem. We are going to generalize the model from a network perspective, from an objective perspective, and from diffusion model perspective, and see where we fail to continue to have the same result. And then I will talk about proof ideas, and I would conclude. Let's just start with this. So this is a slide that any network theory talk has. You have a social network on n people, and people are connected in a network. So that's pretty simple. I'm gonna focus on undirected networks like Facebook. I will talk for 2 minutes about Twitter directed networks as well, but the main focus would be on undirected networks. So here is the diffusion process, and this is the most important slide for the model. At time 0, gray nodes are uninformed, black nodes are informed. At time 0, I inform some node, in this case, this guy over here. And then this guy is going to talk to each one of his friends with probability C. This is a simplified version of the diffusion of microfinance model, because that model is very hard to analyze theoretically, but they have the same fundamental features. So this guy is going to talk to each one of his friends with probability C. Now, you toss a coin, some of them are successful, in this case only this one, and the neighbor becomes informed in period 1. Now I'm going to assume that this guy stops talking after just 1 period. You can easily generalize it to a bounded number of periods of talking. Nothing would change. If you have unbounded number of periods of talking, then the problem becomes irrelevant, because at the end of the day, everyone would be informed if you have just unbounded. So let's focus on this. So Alex is going to talk to his friends with probability C, and then he's going to stop talking. Now this new friend who was informed is going to talk to his friends with probability C again, and then he's going to be successful in talking to these 2 friends, and then they're going to talk to their friends with probability C in the next period. Some of them are going to be successful, and then this is the newly informed person. She is going to talk to the only uninformed friend that she has. She is going to be successful, and then in the last step, this guy is going to talk to his friends with probability C. He is unsuccessful. The diffusion stops. Okay, and the black nodes are the set of informed nodes, which is a stochastic set. It depends on the realization of the probability C's, and grays are uninformed nodes. The objective function that Kempe, Clement, and Tardush defined was the size of this black set. I want to see the expected number of people who are eventually informed. What is that? So now, to state the result in a theoretical fashion, we have to define a network model. I'm going to start with the simplest possible network model, which is the Erdős-Cheney random graph. We are all here. Each one of us is going to be connected to the other person with probability d over n. N is how many people are here, and d over n is the probability that we are friends. This is called Erdős-Cheney random graph, and it's nice because the expected number of friends I'm going to have is d. There are n of you. I'm connected to each one of you with probability d over n. I'm going to have d friends in expectation. So I'm going to prove the result for this network. Before proving or continuing, you may easily see that this is a network which is really symmetric. Everyone is ex-ante equal. So the fact that centrality is not as important in this network and random does well might not be as surprising. I'm going to actually show the exact same result for power law degree distributions as well, networks in which you have highly central agents. But this is a very good benchmark because it's such a beautiful object, mathematically speaking, to analyze. So this is my main slide in terms of notation. Hopefully you won't get confused. So what is a seeding strategy? Now I'm teaching you basically Kempe, Clement, and Tardush. This is not ours. A seeding strategy is a function from a network structure, how many seeds you have, to whom you're going to seed. Okay, so one example is degree seeding. You're going to pick the top S people in terms of how many friends they have. One example is random seeding. You're going to pick S agents uniformly at random, and so on and so forth. Now, as a function of your network, how many seeds you have, and your seeding strategy, this is going to define a stochastic set of agents who are eventually informed, the black nodes that you saw in the example. And then the expected size of this object is going to be a function, h of g, s, and f. And then the optimization problem that Kempe, Klermag, and Tardosh proved it's computationally NP complete is this optimization problem. What is the seeding strategy that maximizes this function? Now, I don't know how to analyze this object. It's a pretty complex object. So we are going to define a seeding strategy which is even better than the optimum, and then provide bounds for that seeding strategy, which then would be a bound for optimum. And that's called the omniscient seeding strategy. The way it works is pretty simple. I'm going to assume that not only you know the network structure, but also you know the realization of those probability Cs. You know who is going to talk to whom. And equipped with this information, you are going to inform the top S people. We are going to solve the maximization problem given this information, and it turns out that's an easy problem to solve, or an easier problem to solve. Okay, and any bound on the omniscient seeding, if omniscient cannot do better than X, optimum can also not do better than X. So, before stating the result, I'm going to tell you 2 points, one conceptual and one technical. The conceptual point is this, that what are we doing in terms of, what is the intellectual exercise? I'm going to start with random seeding. I know that if I go to the field and collect the network data, I'm going to observe some imperfect network. And then I'm going to use some heuristics, such as diffusion centrality. So the gap between these two is your practical value from network data. Now, intellectually, and the intellectual exercise here is that suppose you actually had perfect network data, it's going to do better than imperfect network data. And suppose you actually could solve for the optimum as opposed to the heuristic. And even more, suppose you could observe who is going to talk to whom. And then the theorem is going to state that this gap is actually small, the gap between random and omniscient. As a result, anything in between is also small. All of them are open questions. We have no theoretical results for anything in between. So I don't know how to prove that they are even smaller. Now, the theoretical point is that I need one object, which is called superconstant. I'm going to call a function a superconstant if its absolute value goes to infinity. Okay, so think of n to power, 0.1 or log n or log n, any function that grows with n, but the rate could be as slow as you like. Good? Great. So here is the theorem. So remember, I'm going to state the theorem for Erdős-Chenyi random graphs. So I'm going to take one more expectation of that h function. H function was your objective function. Let's take the expectation with respect to the network model. So I'm going to draw a random Erdős-Chenyi random graph, use a specific seeding strategy with certain number of seeds, and measure how many agents are informed. So this cap h function tells you, for a random Erdős-Chenyi random graph, if I give you S seeds and you use the following seeding strategy, what is the expected number of informed people? And here is the first main result. Forget the first, let S equal to little o(n). We will talk about it. If some condition is satisfied, if DC is more than 1, and you give me super constant additional seeds, okay? Keep log n in mind, for example. If you give me log n additional seeds, in Facebook network that's 21, in Indian villages network that's 6. If you give me super constant additional seeds, then the total diffusion of random seeding with S plus super constant additional seeds is going to be eventually more than the total diffusion of omniscient seeding with S seeds as n goes to infinity. Let me finish the theorem and then I would. Okay, and if this condition is not satisfied, if DC is less than or equal to 1, then random seeding cannot actually compete well with the omniscient. But even the omniscient seeding cannot inform more than a vanishingly small fraction of agents. Okay, so I can't compare random and omniscient here, but I know that the total diffusion of omniscient divided by the total number of people in the network will go to 0. So you would have a very small diffusion. So there was a question.
Yes, I think you are missing something here. Right? You have a capital T, the number of iterations you allow for the network to propagate and diffuse itself. You consider
I assume t is 1, and it goes through for any bounded t. The statement would slightly change, but I assume it's not the total diffusion. So t is, if I inform Scott for how many periods he's going to talk to his friends. But the total diffusion process will not stop. It would continue so long as someone has the opportunity to get informed. Okay, but if Scott is the first person who is informed, and he does not talk to anyone, the diffusion stops. So, given the time, let me be a little bit faster. So what is this object here? D is the expected number of friends you have. C is the probability that you talk to each one of them. DC greater than 1 means in expectation you're going to talk to at least one of your friends if you are informed, or more than one of your friends. If this is the case, then random seeding with a few additional seeds, superconstant theoretically, is going to do well. Now this object here, we will talk in the proof. It's just going to make sure that omniscient algorithm is not doing magically well. In fact, if you look at this, it's bounding the number of seeds from above. In simulations, actually, the more seeds you have, the better random performs compared to other algorithms. So it's just a technical thing that we have to add. Now let me tell you a bunch of points. In theory, any small superconstant will do. So log n is virtually, very close to 0 for any network size you imagine. Remember, the log of number of people in Facebook is like 21. So the log of number of people in Facebook is very small. So in theory, this result goes through for any superconstant. But for what value of n the limit result will kick in depends on the choice of the superconstant. So if you choose superconstant to be exactly n, randomly seeding n additional people, the limit result kicks in immediately. If you choose a very small superconstant, it doesn't. And in the simulations, actually log n seems to be an extremely generous upper bound for when these results kick in. So let me tell you one thing about the proof, which is this. So the way the proof works is that, so this is my social network. Let's take an ex-ante perspective. Let's look at omniscient seeding algorithm. So omniscient knows who's going to talk to whom. I'm going to toss a coin for each one of these links with probability C. These are the people who are going to talk to each other. And omniscient knows that. So what omniscient is going to do is that, note, if I inform this guy here, everyone in this connected component is going to be informed, because these are the people who are going to talk to each other. So if I give one seed to omniscient, the omniscient is going to put the seed here. If I give omniscient 2 seeds, it's going to put it here and here. If I give 3 seeds, here, here, and here, and so on. So omniscient is going to pick the top S, in terms of size, top S connected components of this communication network. This is not the actual network. This is the realization of who talks to whom. Random is going to pick each one of these components proportional to its size. It's just random. It's uniformly at random. Okay, so if you do the mathematics, you can, from this, it's very easy. If I know the distribution of the sizes of the connected components of the communication network, I'm done. And that's what Erdős and Rényi did for us more than half a century ago. So if this is more than 1, the distribution of the sizes of the connected components of the communication network is like this. You have a giant constant size component, and all other components are less than log n, or cap O log n or smaller. And if this is less than 1, all connected components are pretty small. So in this world, if I give superconstant extra seeds to random, it's going to hit the giant connected component. So asymptotically speaking, they're going to do the same, because the small components are irrelevant. In this world, even omniscient cannot do anything, because, you can see the bunch of log n size components, but if you don't have, if your number of seeds are not a constant fraction of the network, you cannot do anything. Okay, so the basic idea is that if the diffusion is not successful, being very careful in picking the right agents is not going to help you, because they're not going to talk to their friends. And the connected components of that network are pretty small. Okay, so there is no mathematical innovation here. This is all credit to Erdős and Rényi. Now, there are a bunch of generalizations. I won't have time to go through all of them, but you should criticize this result, because Erdős and Rényi is very symmetric. This goes through for power law networks, networks with clustering, and hundreds of real-world networks that we simulated. If you change your objective to speed of learning, to a speed of diffusion, that would actually change the results a little bit. If you care about diffusion in the first period, then it's very important to actually inform the right people. And then if you change the diffusion model, depending on how you change it, results can change. Let's see how far we can go on this. Scott would tell me when I have 5 minutes, so that's great. That's more than enough. So this is a simulation on Facebook data. This is the same result. The x-axis is number of seeds. Y-axis is total diffusion. This one is for 1% chance that you talk to your friends. The second one is 5%. The last one is 35%. As you can see, except for this case, which we are in the regime of DC less than 1, or DC very close to 1 actually, 1.5% is enough for us to get the result. Random is doing very well compared to diffusion centrality, degree centrality, and omniscient. The surprising result is here, the last one, that random is doing better than diffusion centrality and degree centrality for almost any number of seeds. Okay, so the gray dashed line is random. The other points are diffusion and degree centrality. The intuition after thinking about it or looking at simulations is easy, but there is no theoretical result. So it would be a nice paper to write, which is these people who are diffusion central or degree central, they are all connected to this core of the network, to this big giant component. And these algorithms are just picking multiple one of those peoples, which is just useless after some point. Whereas random once in a while is seeding one of those small components, so it's doing it slightly better because you're going to pick one of those highly central agents anyways. And it's good to go after smaller communities in the network. Now, power law distribution. So suppose the degree distribution in your network is this. So Barabashi and Albert claim that this is a well description of the world for many social networks. There are criticisms on that too, but suppose your degree distribution is fat tail, comes from that distribution where D is your minimum degree and B is the size of the tail. Basically determines how fat is the tail. And then I'm going to construct the network in a Chong-Lu fashion. If you don't know Chong-Lu, no worries. It's just generalizing Erdős-Rényi to any degree distribution. That's the idea of Chong-Lu. And here is the result that the exact same result goes through. The conditions would change because now I have two parameters, B and D. The condition is that if you have an extremely fat tail, B is between 0 and 2. Which is the case for all of the Barabashi and Albert networks, except for electricity grid network, I think. For social networks, collaborators network, and so on, they estimate the parameter to be between 1 and 2. Or if that's not satisfied, if some other condition is satisfied, if you talk to at least this many of your friends, then the exact same result goes through. Nothing would change. And if those conditions are not satisfied, both of them fail, then the reverse result goes through. Even omniscient cannot seed more than a vanishingly small fraction of agents. Now, the perhaps surprising result is that if I have an extremely fat tail, if B is less than 2, which means I have highly central agents, that's exactly the regime at which random seeding does well. So why this is happening? Well, theoretically, if I want to prove the theorem for you, that's exactly this. The previous proof, you have two regimes. We have to borrow some lemmas from different papers and then add a bunch of new lemmas to prove that the exact same thing like the Erdős-Rényi random graph goes through here. But the intuition is actually much simpler than that. So suppose I have a star network as power law, as you can imagine. It's like that. There is one person in the center, and that person is connected to 1,000 people around him. And I give you one seed, and the probability of diffusion is 0.5. Okay. Now, the central seeding is going to pick the center, and the total diffusion would be 500. That person is going to talk to 1,000 friends with probability 0.5. If I randomly seed, I'm almost surely going to pick someone who is on one of the leaves, which means the total diffusion would be 250, because this person is going to talk to the center with probability 50%, and then the center is going to spread the news. What if I randomly seed a few additional nodes? I'm still going to seed leaves. But the point is that now the chance that one of these people talks to the center is 1 minus 0.5 to power their number. this object here, and this exponentially goes to 1. So if I see 4 people, 5 people, I have a 98% chance of talking to the center, and I'm done. Okay, so the idea is that either your network is extremely symmetric, in which case, who cares about centrality, or your network is power law, in which case, your actually random is highly likely to seed the friends of highly connected agents. Now, you should of course be worried about the diffusion model. I mean, this is a very simple diffusion model. Now, this result goes through for any diffusion model which has this feature of, not any, but many diffusion models that have this feature of independent cascade, that if I inform you, you're going to talk to your friends with some probability. Now, this could be in a microfinance fashion, that you choose to participate or not and then talk. It could be like this diffusion games of Evan Sadler's paper, that once you are informed, you update your belief in a Bayesian fashion and then choose to spread the information or not. It could be like this weather insurance paper that has a linear probability model, that if I inform one of your friends, you have a 10% chance to be informed. If I inform 2 of them, you have 20% chance, and so on. And it even works for directed communications. But it doesn't work for threshold model of diffusion. So Kempe, Clermont, and Tardosh basically study these 2 classes of diffusion: independent cascade and its branches, and threshold. And threshold means if I inform Shengu about some information, if I inform Shengu's friends about something, he is not going to be informed unless at least 5 of them are informed. Okay, I need 5 of my friends to adopt a product in order for me to adopt a product. And of course, in that world, random is going to do very bad, because I'm very unlikely to see multiple friends of the same node. Okay, so it's in some sense an unfair comparison for random, because that's not what random is supposed to do. Now, let me tell you just one thing about the directed communication, which is for mathematicians of the crowd might be interesting. Here I cheated in the sense that I coupled the event that Scott is informed and he's going to talk to me with the event that I'm informed and I'm going to talk to Scott. I said both of these are going to happen at the same time. If one of them happens, the other one would happen as well. Now, in directed communication, it could be that Scott talks to me, but I don't talk to Scott. Okay, so you would have a directed communication network. Now, the exact same result in terms of the structure of connected component goes through. You have a strongly connected giant component that if you inform anyone there, everyone would be informed. The key here, the problem here is that, which is mathematically challenging and beautiful, that omniscient is not going to actually put a seed here. Omniscient is going to put a seed here, because I have one node here that if I inform, there would be a path from that node to the strongly giant component, a strongly connected giant component. So not only I would hit the big component, but also I would just get this path, which is better. And then if these paths are long, then random actually is going to fail. So the challenge is to prove that these paths are not long. The previous known bound was root n, which was actually too long. It turns out that you can prove that these paths are actually size O log n. So they are also pretty small. So that's one of the theoretical results that we would get credit for that, especially Suresh. So this is the result for threshold model of diffusion. I'm not going to go through that. For threshold model of diffusion, this result fails. Matthew Jackson and Evan Storms, Matthew was my advisor, and Evan Storms is a student at Stanford. They formalized this result, that this won't go through for threshold model of diffusion. And for speed of diffusion, I'm going to skip. We don't have results that are as exciting, but you can show that in simulations, the speed of diffusion is also fine if you have more than 2 periods. So let me conclude by 2 points. One, this is not to say that network information is not valuable. There are so many counterexamples for that. One of them is this, which is yet another open question, but I liked it and I put it here. Suppose I want to solve the dual of this problem. So some agent is randomly infected with, say, STD or HIV or whatever, or flu, and you want to vaccinate one node to stop the diffusion. Okay, in this world, optimal vaccination is going to pick the center and diffusion stops. If I vaccinate 10 agents randomly, I'm just going to pick the leaves. So there is still a substantial chance that this infected node hits the center and center diffuses everything. So if you want to defend the network, actually, in this case, network information is highly valuable, which is a sad result because attacking the network is pretty simple, just randomly infect people. If you want to defend it, you need this information about central agents, at least in this example. Now, is it the case for all networks? I don't know. But at least in this one example, we know that defending a network requires network information. Finally, as you saw in my early example of microfinance simulation, there are, this is always, in many cases, it's the case that network central seeding performs better than other seeding strategies in a statistically significant fashion. But that doesn't mean it's economically significant in this sense that we talked in this paper. So there is a statistic that, I think, and we think it's a useful statistic to report once you're writing, or once someone is claiming that some network heuristic is a valuable heuristic, you could also report the extra number of seeds required by random seeding, for example, to beat this heuristic. Now, that would give you some pretty useful information about the economic value of the results. Now, for 2 papers of the literature, we calculated this. There is a Python package you can use. But for 2 papers, we calculated this, and the numbers turned out to be 3, 1, 2, 1. Okay, now, in some papers, the numbers might be much more or much less. I don't know. They can't be much less. They can be at most 3 less. But this tells you something about the economic value of the result. As a policymaker, do you want to see it 1 more person, 2 more person, or you prefer to just go after the network data? And I want to conclude by just saying that this result should be seen as a joint rejection of the value of network centrality seeding, network central seeding, and the diffusion model that we have been studying for a long time in the diffusion literature. Okay, because if the diffusion model is different, if it's not SIR, if Taylor Swift does not listen to any of her friends, but she informs a lot of her friends, or Lionel Messi for that matter, then this result will not go through, because then I have to talk to Taylor Swift directly. Okay, but that's not the diffusion model that we are using in many papers of the literature. Thank you very much. I would be happy to take questions if you have time. By the way, this is an illustrator, Harriet, read our paper and painted this illustration a month ago based on that. No questions? Cool.